Okay, welcome to Unit 7. This is our Oceanography 7A, and we're going to talk about basic ocean circulation and how we actually determine that the ocean actually is circulating. And here we have a map of the entire planet, and these are the surface currents, as well as showing you the purple areas where we actually get the formation of deep water currents. And you notice the deep water currents pretty much are centered on the poles, where the surface currents seem to be more centered in terms of equatorial regions. So if you take a look at it, we've got water moving in all directions, and we'll talk more about those later on. The directions on these are a little bit weird because I want to talk more about water moving up the East Coast rather than what this is. This is showing you deeper water, which is why I don't know why they have this one on the surface. But regardless of whether these currents are on the surface, this is more of a deep water flow. It does actually show you some other things, but you can see surface flows are in red, and this is the Gulf Stream going up, and while we actually have palm trees growing here in the United Kingdom because of this warm water going all the way up. You got deep flows, which are the blues. You've got bottom flows, which are the purples, and you can see they actually are in the Atlantic and they're in the Indian also. You have deep water formation up here in the Labrador and the Nordic Sea, as well as the Wendell and the Ross Sea down here. Wind-driven upwelling, we'll talk about those. Mixed-driven upwelling, we'll talk about those. You've got high salinity areas where the rainfall doesn't happen very often. You have low salinity areas where the rainfall does happen. And then you got these Labrador seas. And then we'll also talk about the ocean conveyor, which is throwing all these things together. Okay, so ocean currents move large amounts of water, but they also move the heat. This is the Gulf Stream, and I love this picture. It's actually showing these incredibly warm temperatures down here in the Gulf of Mexico and around the Caribbean, and it moves up the coast of Florida, hits this section of North Carolina, which sticks out, and then gets thrown out in the Atlantic. And you can see cold water, the purples up here, which can actually move down. This is the Labrador current. And it moves down. You can see the Chesapeake Bay, there's the Potomac River, so we're located about right here. You can also see the Great Lakes. But it brings out lots of heat and lots of temperature all the way up the west coast of the United States. So these are wind-driven currents for the most part, and they move in a clockwise direction in the northern hemisphere. They'll move in a counterclockwise direction in the southern hemisphere. This is due to the Coriolis Effect. It also has to do with the fact that the Earth moves this way. That sloshes the water on the equator, the fastest moving part of the Earth, toward this, and then it actually breaks up in the northern hemisphere and then breaks down in the southern hemisphere. And you can sort of see that the cold water is actually moving in the opposite direction. Cold water actually goes farther down the west coast of the Atlantic or the east coast of Europe, and that's true for the Pacific Ocean and the northern part of the Indian Ocean as well. This is actually going to be a picture of the current SST, or the sea surface temperature map, and you can take a look and see temperatures, which the temperatures here are in degrees Celsius. Room temperature is right around 22 degrees, so that green color is right around room temperature. This is sitting more or less close to body temperature, so you can see that there's some relatively warm areas. You can see the warm area goes up farther in the Atlantic, and the cold area comes down farther on this side of the Atlantic, and the same thing for the Pacific. Cold water comes down the coast of California, and it goes up the coast of Asia, and the exact opposite in the southern hemisphere. As the water moves this direction, the Earth rotates this way, water moves this way, and it gets thrown across the Atlantic, it gets thrown across the Indian, and then it moves up, moves up, moves up, and then on the opposite side of the ocean where it moves down. You can't really see it in this section, but you can see it very easily in the Pacific. And then you have the really cold water around the Antarctic, the South Pole, and the Arctic, the North Pole. And remember, we've got a land mass underneath all the ice down here, and under here we have the Arctic Ocean. Okay, density are deep-driven currents, and we'll talk more about those things later on. And they both redistribute the water as well as the heat, which actually cools down the tropics as well as warms up the poles. It would be a totally different planet if we didn't have this motion of heat as well as water. And this is Earth Null, which I think I've shown you before. this will actually open up. It's not good. Let's do it the opposite way. Earth null school, and instead of wind, or instead of air, let's go to ocean, and instead of waves, let's go to currents, and instead of the whole looking at the earth as round, let's look at it equatorial. And if you take a look, this is the present surface currents of the ocean, and you can, actually that's not what I want to do. You can, where are they? You can download, but you can actually see this Gulf Stream water moving up. You can also see these counter currents, which we'll talk about later on. This thing is where we actually, you can see it sort of moving this direction, and what it'll do is it'll actually bring cold water and bring it down, or it'll actually have warm water, which will pop up top, and fishermen actually look for cold water. Cold water, again, has higher oxygen, higher nutrients, higher plankton, so that all drives the food web. It brings in smaller fish, which brings in medium fish, which brings up larger fish. So cold water is what the fishermen look for, and that's why, if you remember the perfect storm, they're up here in Labrador, this cold water where they were going for, I forget if they're going for marlin or swordfish or something. But this is earthschool.net, then click Earth, pick Ocean, pick Currents, and we'll talk about this site later on. Okay, here's a picture of both surface currents and deep water currents, and you can actually see that this is the most dense body of water, and you can tell because it's the lowest. This one looks like it's next lower. This one right here is the next, and then this North Atlantic deep water, and then we can get Mediterranean Sea, which is probably this one. But you can see these oceans that are actually within the ocean, moving large bodies of water, moving very cold temperatures closer to the tropics. And remember, the equator is going to be located about right here, going underneath this part of Africa. So it brings cold water up towards the tropics. It also brings warm water up toward the poles, or down toward the poles. Measuring ocean currents, that guy's not supposed to be there yet. You can do a direct measurement where you can actually put a buoy out there, or you can put something in the water. This is a buoy. Notice that they're actually, they can be battery powered, which the old ones could have been. Actually, way back when, they didn't have any power. They were just powered by wind. And they'll do temperature, they'll do wind speed, if you have something in the water like these, which will actually pull up the surface current speed, they can do temperature, they can do wave height, bouncing up and down. All that stuff is direct measurement. You can also do it indirectly from satellites. You can do it from ships, actually looking at sea surface height and look at the bottom of the ocean. So basically floating objects and instruments, fixed instruments are direct, and then this way we can do satellite data, we can do Doppler effect flow meters, we can do chemical tracers, and we can do distinctive water masses, and that's the end of first block. This used to be a clickable version. The clickable doesn't work anymore. The site got rid of it, but basically you've got satellites that go up and look at the sea surface. You have satellites that can actually go down into it. You can have buoys on the surface. You can have satellites beam the data down to your lab or your house. You can have boats go out and do things. You can have submarine buoys. You can have buoys at the surface. You can have ones that are tagged at the surface that go all the way to the bottom. You can have buoys at the surface, again, going down to the bottom to actually figure out deep water flows. You can actually put something down at the bottom of the ocean to actually look at speed or density or pressure or whatever you want, but you can do them directly or indirectly. Topaz, this is actually showing you the topaz right there, but this is the Jason. This is Jason 2 and Jason 3. They're all up there. Topaz actually has a nice circular orbit, which doesn't look like it's a circular orbit on a flat Earth, but if you rounded this Earth like we did in that Earth null school, you could actually see this thing is going around the planet. And if you look at all the orbits, the topaz goes down, comes up, goes down, comes up, and the Earth actually rotates this direction right underneath this orbit, and within a period of about 2 days the topaz can look at the entire surface. This is actually another website that actually shows you the location of some satellites. This is real time. And this is, you can zoom in and see exactly where these things are. Again, we're located right here, DC, a little bit lower. You can see there's really nothing in our sky, but you could watch this. You can do a 3D map that is clickable and movable. You can look at a planetarium, which actually shows you the night sky. You can look at the celestial sphere, which is above you, and you can get information on satellites. This one's actually looking at Gainesville, and I'm not sure where it's getting that, probably from the computer, but you can probably locate other locations like Dumfries, Virginia, or Woodbridge, Virginia, wherever you live. Okay, so surface currents caused by friction and drag of wind. That earth null school that I showed you looks like this. And you can see there's the Gulf Stream, there's all the countercurrents we were talking about, and we'll talk about those later on. Surface currents are similar to the global wind pattern. This is where continents actually affect the water, where it doesn't affect the wind as much. And other factors, gravity, which is pulling down the water, friction, water against other water, and maybe against the wind, Coriolis Effect, moving things to the right in the northern hemisphere, south, clockwise. And then this is an interactive map, which I will click. This is something you can't see on an Apple. So ocean currents look like this. Red's actually showing you warm water moving away from the tropics, and blue's showing you cold water moving from the poles. You can throw up wind patterns, and you can see that the wind is moving to the right in the northern hemisphere and to the left in the southern hemisphere, and that helps push this water in this direction. And then you can throw both of them on there and actually see the wind blowing the warm water up and blowing the cold water down, and we'll talk about these currents as something else really soon. And the last one I want to show you is this one, another shock wave. And this actually shows you circulation close to the equator. These are called convection cells. Then we can throw surface, and you can see it moving to the right. These are where the northeast trade winds. We live in the west, and why our weather comes pretty much from the west coast, because we live in the northwesterlies. And then high altitude, and then we can actually clear all those, but I thought we could actually throw on all the convection cells on this one. But that's pretty much it, I think. Let me click it. Yep, there's the stop, and that was 7A, oceanography, how we determine these currents. Thanks for stopping by.